Welcome to the massive open online course on Aspen Plus. Today we are going to discuss about the economic analysis by using Aspen Plus software. As we all might know, that the cost involved in designing, developing and commissioning of a process plant, the entire project involves huge cost. And this cost can be divided primarily into two parts. One is the capital cost and other is operating cost. The capital cost can further be divided into direct and indirect cost. The direct costs, they are of purchasing equipment, the installation, the instrumentation, control, piping, electrical system, buildings including services, service facilities, land, yard improvements, and many other things that I might have missed out. And indirect cost, they are mainly legal expenses, construction expenses, constructor fees, and contingency. So these include in the capital cost portion. On the other hand, the operating costs include mainly two types. One is the manufacturing cost, another is general cost. Manufacturing cost may further be divided into three parts: the variable cost, fixed charges, and the plant overheads. Variable cost means the cost which vary with time, that is raw material, utilities, the cost for that, operating labor, direct supervision, operating supplies, maintenance and repairs, laboratory charges, patents, and royalties. Whereas fixed charges are depreciation, financing, local taxes, insurance, and rent. And general expenses are administration expenses, distribution and marketing, and research and development. So these are the general expenses. Now, Aspen Plus has the capability of analyzing the entire operating cost and capital cost, and it can give you a report after you do the simulation that will help you to further design the plant and take some informed choice before you develop it. So today we will learn these things. Now it is better to take an example problem, understand its features, and then try to analyze its capital cost and operating costs, etc., so that we can learn the whole thing in a better manner. So we will directly go to an example problem, solve it, and while solving, we'll learn the entire process. So this is the example problem we have. We have to find the economic attributes of an acetic anhydride production unit. Okay, that we will demonstrate. Problem is, we have fresh feed. The temperature, pressure, and flow rate has been given. It is mixed with a recycle flow. So there is a recycle flow in the plant which will be mixed with it. Now, we do not know at this moment what the recycle flow is. It will be identified later in the problem statement. The mixed flow, that means the acetone and the recycle flow, that mixed flow is heated to 1035 Kelvin through a fired heater which is operating at 1000 degrees centigrade and zero pressure drop. So basically we have this feed, we have this recycle, they are mixed over here and they are fed into a fired heater. Okay, and this fired heater is operating at 1000 degrees centigrade. Now this fired heater is an utility. Okay, before it is fed to an adiabatic PFR, so it is fed into a PFR which is adiabatic, and the dimension of the PFR has been given 3 meter long and 1 meter dia. The following kinetic, that is a power law type reaction, holds inside the PFR to produce ketene and methane. So these are the products of PFR. So this is the equation where the kinetic factor and the activation energy they are given. The products are stepwise cooled first to 140 degrees centigrade and then to 90 degrees centigrade. So after PFR, we will have two coolers in series, and here it will be 140 degrees centigrade and here it is 90 degrees centigrade. Stepwise, it will be cooled. And in both the coolers, there will be zero pressure drop. And they will be in series before they are sent to a multi-stage compressor. So there will be a multi-stage compressor over here. Okay. So this is the chain of equipments we will employ. Now the first cooler sinks the heat to a low pressure steam generation unit. That means actually, as we know, the PFR is operating at a very high temperature. It is 1035 Kelvin, and then it is fed to a PFR. So the outlet of PFR will be quite hot. Now we are not going to lose that heat. Rather, we will use that heat to generate some steam, okay, which will be used for something else. So this is what we will do. We will use the first cooler to generate some low pressure steam, and the second cooler uses natural air as a coolant. So at the first cooler, the temperature drops down to 140 degrees centigrade, and the second cooler from 140 to 90 degrees centigrade. So in that cooler, we will use air, natural air as coolant. The multi-stage compressor, which is isentropic model with ASME method, it has 4 stages that raises the pressure to 29 bar. So the compressor is raising the pressure to 29 bar. Stage 1 and 3 run on zero heat duty, while 2 and 4 they run with an outlet temperature of 150 degrees centigrade. So this is the stepwise operation of a multi-stage compressor. The stages run on electricity, so this is the utility again, while the coolers use natural air. Because as you know, the compressor, it develops a lot of heat energy because you are pressurizing the gas over there, so it will generate a lot of heat. So you need the cooler. So the stages run on electricity while coolers use natural air. The gas mixture is then passed through 2 consecutive rad-frac columns in series. The first column, it has 14 stages, and 7th being the feed stage, it has a total condenser. Its reflux ratio and distillate to feed ratio has been given. Now we have to assume the column running at a constant pressure of 29 bar. So the pressure doesn't change in the column. So it is same as what it has been in the compressor. The condenser uses refrigerant 4. So in the utility section, we know there are 4 types of refrigerants. Refrigerant 1, refrigerant 2, refrigerant 3, refrigerant 4. So condenser uses refrigerant 4. While the reboiler heats up with high pressure steam. Again, we are using another utility, high pressure steam. The distillate is fed to the second column, while the bottom product is recycled back as recycled stream as mentioned in the beginning of the problem statement. So we remember that acetone was being mixed with another recycled stream. So this is the recycled stream. So recycled stream is coming back from the bottom of the first column, and it is mixed with the acetone before it is fed to the fired heater. Now the second column, that means distillate from the first column is being fed into the second column. So the second column is similar to the first one with the following changes. Only 3 or 4 changes are there. One is reflux ratio. In the first column it was 6. In the second column it is 4. The distillate to feed ratio, it is 0.5. In the first column it was 0.387 as far as I remember. Here it is 0.5. And the entire column pressure is at 28 bar. In the first column it was 29 bar. Here 1 bar is reduced. And the reboiler heats up with low pressure steam. In the first column we were using high pressure steam. In this column we are using a low pressure steam. So these are the 4 changes we will do in the second column. The distillate is primarily methane, so it's a useful product for sailing, while the bottom product is primarily ketene. So ketene is one of the reactant for producing acetic anhydride. So this ketene is fed to the CS tier, where acetic acid, whose flow rate, temperature and pressure has been given, is also fed. So in the reactor we have one way ketene, another way there will be a supply of acetic acid. The CS tier operates at 75 degrees centigrade and 15 bar, and its residence time is 1.5 hours. An equilibrium reaction between the ketene and acetic acid produces acetic anhydride. The CS tier is cooled with standard cooling water. Again, we are introducing another utility, that is cooling water. Now all these utilities are available in Aspen Plus, so we have just to call them and use it in our process. Property method has been given, Will's NTH property method, that will be used in this case study. And we have to estimate the missing parameters with UNIFAC. So in the property parameter, we have to tick that, estimate the missing parameters with UNIFAC. Now there are certain information, added information has been given, like the operating life of the plant is 20 years, because this will be very necessary for cost calculation. Okay. So operating life of the plant is 20 years. The length of plant startup is 20 weeks. So within 20 weeks, it will be developed, commissioned, and it will be starting up. The starting day of the basic engineering is 1st July of 2025. So these are the few information that we have to feed in Aspen Plus costing options. Now, as we are looking for some costing options, so we have to provide some market price. Okay. For instance, we will procure acetic acid and acetone. We have to supply this thing to the process. Okay, so we have to purchase them. And their cost is $600 per ton for acetic acid and $1,200 per ton for acetone. So these are the money that we have to spend. Whereas acetic anhydride and methane, they are sellable product. Right? So if we sell them in the market, this is the market price. For methane, it is $6,150 per ton, and acetic anhydride, it will be $1,000 per ton. So by selling these things in the market, we will generate revenue. Okay, so we have to use this pricing information in the costing options. And there are certain utility alterations that we have to perform, like in the cooler, we will use a floating head shell and tube. Cooler 2, we have to use air cooler. Column 1, we will use bare pipe immersion coil heating, and there will be no overhead and bottom splits. Heater and mixture also, there will be some changes, which we will understand later while we solve the problem. So we shall open the Aspen Plus window and we will begin our solution. Okay, so this is the Aspen Plus command window. First, we have to select the components. So the first component is acetic anhydride. So let us find this acetic anhydride. This one is the one which we have to choose. So let us name it as acetic anhydride. Okay, rename. Then what else? We have acetone, which will produce ketene and methane. So So this is acetone. Okay, it is acetic acid, not acetone. But anyway, acetic acid also we will need in the CSTR, so we keep it. And acetone we can write like this. Okay, and we have ketene. What else? We have methane, right? So methane, and we also need cooling water. So we have to write water also. Okay. Right. Now we have to choose methods. And if you remember the method, so we have to use Will's NTH property method, and we have to estimate the missing parameters using UNIFAC. So we will use Will's NTH, and we have to go to Wilson and estimate using UNIFAC. Run. Okay. So the results are available. We can go to the simulation. Okay. Now let us pull the blocks from the model palette one by one. First, we have to use a mixer which will mix the acetone and recycle flow. And then we have to use a fired heater, and then a PFR, and then two coolers in series, and finally one multi-stage compressor. So first we will use a mixer over here. Then we will use a heater, and the same heater we will use twice over here because we have to use them as a cooler. In between we have to use a PFR, and then we have a multi-stage compressor. So these are the things that we will need. So let us rename it as mixer. Let us rename it as heater. This one is PFR. This one is cooler 1. This one is cooler 2. This is multi-stage compressor. Okay. Now let us connect the flows. Okay. So first rename them again. We will pass acetone over here. So let us write acetone. Then recycle stream will join from there. We will settle recycle stream later, and combinedly it will be a feed that will be heated, and it will go in as PFR in. This will be PFR out. That will be cool 2, say cool 1 out, and this will be cool 2 out, and this one let us write as M comp out. Okay. Okay, so first we have to fix the acetone. Okay, so what is the flow rate and temperature pressure of acetone? It is 1000 kg per hour, 25 degrees centigrade and 1.6 atmosphere. So it is 25, 1.5 atmosphere and 1000 kg per hour, right? So it is 1000 kg per hour of acetone. Okay, so it goes to the heater. We have to specify the heater specifications, and heater operates at 1035 Kelvin with zero pressure drop. So it is 1035 Kelvin, zero pressure drop, and we have to use a fired heater, right? So we have to use a new utility, fired heater 1000. Let us name it like this. And this is the fired heater. The fired heater inlet temperature is 1000 degrees centigrade. So this is exactly what we were looking for, right? Then let us go to the PFR specification. In the PFR, the reactor type is, I think it is adiabatic reactor. Yes, it is fed to an adiabatic PFR, 3 meter long, 1 meter dia. So it is adiabatic reactor. It is 3 meter long and 1 meter dia. Okay. Now go to the reactions. In the reaction, we have to set a new reaction, which is a power law. This is a power law type reaction. This is a power law type of reaction. And that reaction is, okay, we have to define the reaction over here. So let us define the reaction input, say new, it as acetone, 1 mole of acetone produces ketene and methane. Okay, and kinetic properties we have to provide over here. This is 8.19733 10 to the power 14. So 8.19733 E14, and this is the activation energy, kilojoule per kilomole. So this one is kilojoule per kilomole. And reacting phase, actually this is very high temperature, 1035 Kelvin. So it will be in vapor phase. It cannot be liquid phase at all. Okay, so that's how we specify the PFR. Now there will be two coolers in series, and it will be cooled first to 140 degrees centigrade and 90 degrees centigrade via two coolers, both zero pressure drop. Okay, so here it is 140 degrees centigrade and zero pressure drop, and then this will be 90 degree with zero pressure drop. Okay. Then it goes to the multi-stage compressor. Now the first cooler sinks the heat to a low pressure steam generation unit, while the second cooler uses natural air as a coolant. So we have to use the two utilities. In the first case, low pressure steam generation unit. In the second case, natural air. So let us go to the cooler 1 and 2 once again. Use utility ID, new utility. Let us name them as generation of low pressure steam. Okay. And here, yeah, low pressure steam generation. Okay. And then open cooler 2, go to utility, and here also the new utility, it is air, and we have to choose air, this one. Okay. Now go to the compressor. So in the compressor, it says it is isentropic model with ASME method, has 4 stages that raises the pressure to 29 bar. So 4 stages, isentropic using ASME method, and the pressure increases to 29 bar. And what else? The stages 1 and 3 run on zero heat duty, while stages 2 and 4 run with outlet temperature of 150 degrees centigrade. So we will go to the cooler. Here we have stage 1, stage 2, stage 3, and stage 4. Okay. And the specification for stage 1 and 3 heat duty, and for 2 and 4 it is outlet temperature. So heat duty, zero heat duty for 1 and 3, and outlet temperature 150 in 2 and 4. So we'll place 0 and 0 over here, whereas here 150 degree centigrade, and here it is 150 degree centigrade. Now the stages run on electricity while coolers use natural air, right? So again, the utility, this is air, this is air, this is air, and this is also air. Okay. But the stages itself, it uses electricity. Okay. So the stages that use a new utility will use electric, which is electricity. Okay. So this is electricity. This is also electricity. This is also electricity. This is also electricity. So all the stages work with electricity. So compressor is fixed. Okay.